Welcome to this session. This session is all about working some AP problems that are stoichiometry related. I'm not going to promise you that gas laws won't show up from time to time, maybe some freezing point depression, so you may learn a few new skills along the way, but essentially the best category for these problems is under the heading of stoichiometry. And we have lots of them to work, so the best way for you to do this is to make sure that you have the AP worksheet key that is produced by the National Math and Science Initiative with permission from the College Board. And if you do, then you have a numerical listing chronologically arranged by year of the problems that are good for practice problems in class, and maybe you've even worked through some of these. So if you have, feel free to fast forward or jump ahead, do whatever you need to do. But I'm going to go ahead and work through quite a few of them with you so that you've got at least some basis to be able to study for the first test. The stoichiometry test often eats a student's lunch in the very first try because you've never taken a test like this. A test like this is going to have a lot of multiple choice questions with no calculator. That'll be half of the test. Then you'll have 3 free response to work. And everything is timed, so you'll be under some time pressure. Of course, if you're scoring 75% of the multiple choice points and 50% of the free response points, you're doing a fine job. And you shouldn't beat yourself up over that. But most of you are really good kids who have been used to listening to what any teacher says and regurgitating that on Friday's test. These tests will cover a lot more class time, so you won't have as many of them, but they could indeed be a bit of a shock to your system until you get used to it. But I do promise you'll get used to it. And it's better for you to practice these a few times throughout the year, 12 to be exact, than to wait till the very last minute, right before the AP exam, to learn how the AP exam is structured, how to take one, how to grade one, etc. So we're going to dive in here with the 1982 edition of the stoichiometry problem, which reads water is added to 4.26 grams of UF6. I recommend that you circle pertinent information so that you don't have to spend precious seconds rereading it. The only products are 3.730 grams of a solid containing only uranium, oxygen, and fluorine, and 9.70 grams of a gas. The gas is 95% fluorine and the remainder is hydrogen. Well, therefore, 5% hydrogen. We might need that. So the first thing they want us to do is, from this data, determine the empirical formula of the gas. Okay, so we're only talking about the gas, so we know it's some variety of H and F. So we're looking for the subscripts on the H and the subscripts on the F. So let's just dive in, because when in doubt, find the number of moles of something, anything. So from this data, we know that fluorine is equal to 0.95, 0.970 grams times the fact that it's 0.95% of that 0.970 grams that would be the fluorine. And so when we multiply that out, you need to be punching the buttons. Do not just watch me punch buttons. This is a lot like learning to play a musical instrument. The more you type on your calculator, the faster and more accurate you become. So this is going to be 0.9215 grams of F then, because this was grams of sample, so you don't get confused later. And that then divided by the molar mass of fluorine, which you need to get very familiar with the College Board periodic table. It's on our wiki page. I'm sure you already have a copy or 2 or 3. Hopefully you have some stashed in various places around your house. But we're going to divide by that molar mass of 19 grams per mole. And so it's still sitting in my calculator. Get my calculator back. You want to leave everything in your calculator. You don't want to take anything out. And we have 0.0485. I'm not worried about sig figs in this problem at the moment because ultimately my answer is going to be an empirical formula. Let's do the same thing for hydrogen. So that means that same 0.970 grams of sample times the fact that it's 0.05, which is 5%, hydrogen, gives us 0.0485 grams of hydrogen divided by 1.01 grams per mole. gives us 0.048, which is really close to 0.0485. Pen didn't want to work. Sorry about that. 0.0481. Nope, actually 0. At which time we figure out, yeah, we've got basically an HF here. We have 1 mole. So 1 to 1 mole to mole ratio. So these are close enough together that you could call that 1 to 1 mole to mole. So therefore the empirical formula is. So next they ask me what fraction of the fluorine of the original compound is in the solid and what fraction is in the gas after the reaction. Well, the fraction of fluorine in the original UF6 needs to be found. Let's do that first. So it's 6 times 19 per fluorine divided by the fact that the molar mass of the whole mess is 238. Again, use the periodic table. When you're old like me and do this for a living, you kind of memorize some of these molar masses. So 238 plus, again, the 6 times 19. This is the total molar mass in the denominator and the mass of just fluorine on the top, the 6 fluorines. And so you come out with my calculator. 19 divided by paren 238 plus 6 times 19. Notice the brilliant use of the parentheses keys. Get good at that. So that comes out to be 0.324. That's a fraction, so it actually doesn't have any units because it's a fraction. That means that the number of grams of F in the original US6 is going to be equal to 0.324 times the mass of the sample, 4.267 grams of the sample, which equals, and again, leave it all in your calculator. Did I get that right? 4.267? So that is going to be 1.38, I guess is what we'll call that. F6. Oops, that's not what I meant to do. I need to click that one. Okay, so why did I do all that? Let's recap. What fraction of the fluorine of the original compound is in the solid, and what fraction in the gas after the reaction? So the fraction of the fluorine in the original, UF6, is 6 times 19 for the 6 times the molar mass of the fluorine over the total molar mass, and I come out with 0.324. So now I need that in grams. So the grams of fluorine in the original UF6 is that fraction of 0.324 times the grams of the entire sample, which is equal to 1.38 grams in the original UF6. So the gas has 0.9215 grams. Where did I get that? Of fluorine. Oh, that's the 95% times. That's one of the first things I did. There was, that number came from part A, right up there, right up here. Okay, so that many grams in the fluorine. Therefore, the fraction of F is going to be equal to the 0.9215 grams over the total mass, which was the 1.38 grams that was in the UF6. And that comes out to be 0.9215 divided by 1.38. And I come out with 0.67 essentially. So 0.67 in the gas. Therefore, the solid produced has the remainder of 0.33 fluorine in the solid. So there's the answer to your question. Why they're in fractions is why these are naked numbers. All right, so one more time from the top. I'm going to make this a little bit bigger so you can see all of it. What did we do? They gave us an amount of UF6. They gave us an amount of a solid, and they told us that they gave us an amount in grams of a gas as well. And they gave us that hint that the gas was 95% fluorine. So let the problem lead you. You're going to hear me say this over and over as we work through AP problems this year. Let the problem lead you. The authors, and I used to be one, the authors have been instructed to write a logical problem that follows a logical chemical problem-solving process that's taught in most textbooks across this country as well as others. So the first thing we did was take our grams of sample and multiply it by the 95% for fluorine and the 5% remaining, obviously, since that has to add to 100%, that was H. And so we turned both of those into moles, and we got a mole-to-mole ratio, and we determined that the empirical formula is HF. We'll probably have to use that later. Then they wanted to know what fraction of the fluorine of the original compound is in the solid and what fraction in the gas after the reaction. Well, to do that, it's best to know the amount of fluorine in the original UF6. So by mass, that is simply 6 times 19, since there's 6 fluorines, and they're 19 each, over the total, so this is part over whole, over the total of 238 for the uranium plus that 6 times 19 for all those fluorines, and you come out with 0.324. So the grams of fluorine in the original then is 0.324 times the mass of that original sample. So that was your UF6 sample. That came out to be 1.38 grams of fluorine in the UF6. So the gas has a mass of 0.9215 grams of fluorine. Therefore, the fraction of fluorine is 0.9215 over the total of 1.38 grams in the UF6 that were present. So the fraction of the fluorine from the original sample that ended up in the gas was 2/3, or 0.67, and if you wrote 2/3, that's fine. And so the solid produced then has the rest of that, which is 1 minus 0.67, which would be 0.33. So that the total adds up to 1.0 for the whole. All right, so a little bit of a workout on your basic 5th grade percent skills, but not too evil so far. Now we want to know, what is the formula of the solid product? Okay, so in order to do that, I got to realize what the solid product contains. It contained uranium, and it contained oxygen, and it contained fluorine. I gotta say UFO was way more fun, so I'm gonna do it in that order. Give a girl a little bit of fun here. All right, so the mass of U would be the 4.267 grams of UF6 they told us at the beginning, minus the 1.38 grams of F that we solved for earlier. Way back up here, right here. And that comes out to be 4.267 minus 1.38, 2.887. So I'll call it 2.89. That many grams of uranium. And then the mass of the fluorine is going to be equal to the 1.38 grams of the fluorine in UF6. The fraction, a third of it roughly, ends up in the solid. So that is 0.46 grams of F. And then the mass of O is what remains. It's the rest. The rest. So minus the sum of the 2.89 grams of uranium plus the 0.46 grams of fluorine. Simple subtraction. And that equals 3.73 minus 2.89 minus 0.46. Well, that didn't work out very well. Oh, I missed a decimal. Dang it. Try that again. 3.73 minus 2.89 this time minus 0.46 equals 0.38 grams of oxygen. Okay, so what was all of that good for? All of that was good for me to get grams so that I can calculate moles, because when in doubt, I need the moles of everything. So I need a little more room here. So moles of UFO are going to be the 2.89 grams of uranium, which is calculated, divided by its molar mass of 238. And fluorine will be the 0.46 grams that we just calculated, divided by its molar mass of 19. And oxygen will be 0.38 grams divided by 16 for its molar mass. So here we go. 2.89 divided by 238. And if you left it in your calculator, that's all fine. We'll agree close enough here at the end. So 0.2 mole of uranium, 0.46 divided by 19, 0.242 mole of fluorine, and 0.38 divided by 16, 0.024 moles. Okay, I missed a zero back here, didn't I? Look at my screen and see that. That's my worst habit. You'll get used to it. I do it a lot. Alright, so now I have moles of everybody. I can see that I've got pretty much a 1 to 2 to 2 ratio. That's pretty simple. If you need to see it mathematically, you divide everybody by the smallest. So 0. So you come in and divide everybody by the smallest. This one we can kind of eyeball. So therefore, I have U, O, 2, F2 to put it back in the way they presented it. I just thought UFO was more fun to do. Alright, now, finally, what do they want me to do? Write a balanced equation for the reaction between UF6 and water, and assume that the empirical formula of the gas is the true formula. So UF6 is going to give me what I just figured out. UO2F2, and again, let the problem lead you. You just figured it out for a reason. And we figured out earlier it was going to be HF. So now what? What's the scariest looking thing there? Maybe the UO2F2? Oh no, when I look at that, I'm looking over here at UF6 going, I have F in 2 places. So let's think this through. We've got 1 U on each side, 2 oxygens. So let's start by putting a 2 there so we get our 2 oxygens. And what do I have now? I've got 6 F's on the left, I've got 2, and I've got 4. Oh, but I need a 4 right here to get 4 H's. So that gave me 4 F's, 2 more F's, so 6 F's on each side, 2 O's on each side, 1 U on each side, and we are done. So there is your balanced equation. And I do believe that was the end of this problem. So let's go back and score it, because you're new at this. It's important that you understand that If you have your calculator in your hand, the problem is usually either worth 9 or 10 points. This one was worth 9 points back in the day in 1982. I'm going to make this bigger. If you get 5 points out of this 9, you are doing great. If you get 4, you are not so shabby. But great is to get at least half of the points. And since you can't really divide 9 evenly in half, I would go with 5 points. So if you got this far, this was worth 2 points. I suspect they gave you a point if you could get to moles and another point for if you knew what to do with it once you got there. That was worth 2 of the 9 points. And if you could calculate this, that was worth a point. And if you could calculate this, that was worth another point. So if you could get that far, you're in really good shape. This one was a little bit trickier, just had a lot more to think about. If you got both of these, that was worth a point. If you got this far, that was worth a point. There was 1 point for the set of moles. And 1 point for a final answer. So you know your teacher chants all the time, show your work, show your work, show your work. I realize that some of you are so very smart that you could have just done all of this in your calculator without writing a bloody thing down. More power to you in multiple choice. You won't have a calculator there, but more power to you. But look at the points and look at the way this is set up. Part C was worth 1, 2, 3, 4 points, and if all you wrote down was the final answer, you lost 3 of them. So you do have to show intermediate steps along the way. Finding the number of moles is always a good one. Finding a multimole ratio in this case was also a good one. And then finally, the easiest of all is this point for getting a correct balance equation. So that's how it's scored. Again, if you got 4 or 5 points out of this, you are doing really good. If this was your very first try and you even got 2 points out of this, that is not totally disgraceful. If you scratch your head and don't know where to start, hear the sound of my voice over and over saying, when in doubt, compute the number of moles of something, anything. Just get started. Just find the number of moles of something. It's going to come in handy. And then if you think about empirical formulas, they're multimole ratios, very simple multimole ratios. We do not write H 0.048 F 0.0485. We simplify that by dividing both by the smallest and coming out with basically a 1-to-1 ratio. Considering this was experimental data, it's never going to come out perfect, and you shouldn't expect it to come out perfect. All right, let's try another. Again, I say, what you really need to do is you need to pause me, and you need to work through this problem yourself first. Ideally, you would have worked through this problem before you even got to this recording. Maybe in class. Maybe as a homework assignment. So this is like, maybe you're just listening to this so that you can review for your test and do good. But let's get going on this one. All right, when you see the question mark, you got to know you're in trouble. You're going to have to figure out what the value for that question mark is. But let's read the problem first. 3 volatile. Okay, let's talk about volatile. Volatile means stinky. If there's an aroma, it also means evaporates quickly. So if you've ever put gasoline in your car, you smell it as it's coming out of the pump. That's a very volatile liquid. It means that they evaporate very easily, but they're not very attracted to each other at the molecular level, so they escape the liquid phase very easily, and usually the warmth of the environment is enough to help them have enough thermal energy to evaporate. So 3 volatile compounds, X, Y, and Z, each contain element Q. The percent by weight of element Q in each compound was determined, and some of the data obtained are given below. So they give me a piece of information about vapor density. It's the same as gas density. The difference between a gas and a vapor is that a vapor comes from something that was a liquid at room temperature, like gasoline, like rubbing alcohol, like perfumes. So the vapor density of the compound is just the density. But if it's a vapor or a gas, it's going to be given to you in grams per liter. That's important to know. Of compound X at 27 degrees Celsius and 700 millim. Okay, look at that. You have a temperature and a pressure. That means there is a very good chance that you are going to do PV-NRT. PV equals nRT, the ideal gas law. So you need to start marking these amounts up and underlining them so that you can find them quickly. And it was determined to be 3.53 grams per liter. That's how you report densities of gases. If it's a liquid or a solid, you do grams per milliliter. Calculate the molecular weight of compound X. Well, hopefully in first year you were introduced to the molar mass kitty cat, but if you were not, then let me introduce you. Molar mass, for anything that was in the gas phase, and I know I'm in the and temperatures, it is equal to the density of the gas, which we'll symbolize with a D, times R and T, as in PV equals nRT, over P. Because every good cat, again, this is the molar mass kitty cat. I realize that's spelled with a C, but it's more fun with K. So this molar mass kitty cat, any good cat, if any of you ever watched a cat before with its elimination habits, puts dirt over its pee. I'm not proud of this, but it actually works really quickly in solving clean problems, and you haven't seen the last of it. So we're going to put in the density of 3.53 grams per liter. Is the 0.0821 liter atmosphere mole Kelvin, and that's going to dictate our units for the rest of this calculation. While we're here in this 0.0821, you're going to use it a lot, so let's just program it into your calculator. So we go 0.0821, you get it in your calculator. Right above your on button is a store button, and an arrow comes onto your screen, and let's call it R. And the R lives above your multiplication sign button. Press enter to make it stick. So now I don't have to risk typing that wrong or be annoyed by typing it over and over again as you sit and work problems. Always good to do a lot of your constants that way for homework assignments. The T has to go in as Kelvin. So this will be 27 plus 273, and I can do that in my head. That's 300 Kelvin. So that is 300 Kelvin. And the P has got to be in atmospheres. There are 760 millimeters of mercury in 1 atmosphere, so we have a fraction of an atmosphere that is equal to 750 over 760 atmospheres. So my atmospheres will cancel, my kelvins will cancel, my liters will cancel, and I will come out in grams per mole, which is beautiful if you're looking for a molar mass. So therefore, the molar mass of X, compound X, is equal to 3.53 times alpha R, we're just recalling that number, times 300. I like to get that numerator first, and then divide it by, open a paren, 750 divided by 760. If I lose you anywhere, remember you can rewind and listen again. Alright, so we come out with 88.1. Is that a good number? But when I actually calculated with it, I used 3. So let's go with 3. So we should come out with 88.1 grams per mole. So that's what goes up here. You don't have to put it up there. It's just kind of nice to be able to look at it. So the next thing they want me to do is determine the mass of element Q obtained in 1 mole of each of these of the 3 compounds. Okay, so if you give me a molar mass and then you give me a percent, I can make all of these into fractions by dividing by the 100, moving the decimal 2 places, and multiply, and I'll get the mass in each one, X, Y, and Z. So for X, it's 0.648 because it was 64.8% times the 88.1 we just found grams per mole, and that's going to give me 57.1 grams. This was times 1 mole, so the moles are going to really flop out of Q. And then for Y, it was 0.730. So that's, oh no, I take that back. It's up in the table, it's 104 grams per mole. And so that is 75.92. I'll call that 75.9. And for Z, it was 0.593 times 64. 37.95. Let's call that 38. All right, ideally, I would now peruse these numbers. That's all I have to do. The next piece is going to have me peruse these numbers. Calculate the most probable value of the atomic weight of element Q. My inclination would be that the smallest number up there is 38, and I would hope the rest of them were all multiples of 38, but clearly they are not. So what am I going to do? Well, I need to think logically. I know that's painful, but let's think logically. What if Z had 2 Q's in it? Because that'd be the next simplest thing, right? I would love it if Z had 1 Q, and then Q twice, Q 3 times would show up in these other numbers, but I'm not getting that. Because I'm looking at 38 and going, well, that'd be what, 76? So I got 76, no problem, but 57 is not fitting that pattern at all. So the next logical thing to do is go the other direction and say, okay, what if there are 2 Q's there? So 1 Q would have weighed 19. So let's see if that works. And this is trial and error, but this is thinking logically. 38 divided by 19 would be 2. So 76 divided by 19 is also going to work and be 4. And then 57.1 divided by 19 comes out 3. Okay, that's nice. So I'm now convinced that Q is 19. So Q is 19 grams per mole since all must contain a multiple atomic mass and 38 is too large. Try half. Okay, so there we go with that one. Compound Z contains carbon, hydrogen, and element Q. When 1 mole of compound Z is oxidized and all of the carbon and hydrogen are converted to oxides, 1.37 grams of CO2, let's start with that. I feel like when in doubt, find the number of moles thing coming on. And 0.281 grams of water are produced. Determine the most probable molecular formula for compound Z. Well, when in doubt, find the number of moles. So let's divide this by the molar mass of carbon, 44.01 grams per mole, and we'll get moles of carbon dioxide. And then this divided by the molar mass of water, 18.02. So 1.37 divided by 44.01. And that's 0.0311 mole of carbon dioxide. Therefore, that's the same number of moles of carbon, because it says carbon, hydrogen, and element Q. All right, so that's 0.0331 moles of carbon. Because there's only 1 carbon for each one of those CO2s. All right, do the same thing with the water. 0.281 divided by 18.02. And we get 156. Can I call it that? Moles. You're going to see a lot of that. Mole H2O. Therefore, see that little 2? Double that, because there's 2 hydrogens for every one of these. So 0.0312. of hydrogen. And now, how do we go get the Q? Because we've got our moles of carbon, we've got our moles of hydrogen. It's looking pretty good. They're 1 to 1. And now, what do I do about the Q? Q, I need the grams of Q. Oh, easy enough. It was a 1 gram sample. Aha, 1 gram compound of Z, so just subtract. So 1.00 grams of Z minus grams of carbon, which will be 0.0311 mole of carbon times 12.01 grams per mole. That'll get me grams of carbon minus, same song, second verse for hydrogen, 0.0312 moles of hydrogen times 1.01 grams per mole for the hydrogen. So 1 minus, open a paren, 0.0311 times 12.01, close a paren, minus, open a paren, 0.0312 times 1.01, close a paren, enter. 0.594 grams of Q. Then we're going to divide that by 19. That's what we figured out earlier. Let the problem leave you. Grams per mole equals 0.0313 moles of Q. Okay, so now we got moles of everybody. 0.0311, 0.0312, 0.0313. Yeah, I'd call that all the same. So it's going to be CHQ for our empirical formula. It's 1 to 1 to 1 to 1 for the empirical formula. Now, what else did they tell me? Let's look back up at the table. Molar mass, that's what I was needing. It wasn't in the word, so it had to be up here in the table. The molar mass of Z is 64. So the empirical mass of CHQ is 12 plus 1 plus 19. I can round these all off. We'll get the big idea here. It's 32. And the molar mass of compound Z is 64. Therefore, the molar molecular formula of compound Z is C2H2Q2. In other words, twice as much. So once you figure out that's a 1 to 1 to 1 ratio, and you figure out that's 32 and that's 64, which is a doubling of 32, then you simply double all the subscripts in the empirical formula to get your molecular formula. All right, so once again, let's go through some point values, because I know you're new at this and you're trying to learn how this is all going to work. So let me minimize this, make this big so you can see it. So this also was a 9-point question. So if you did what I asked, which is you've already worked this before you listened to this, or you paused and you did your best to work through it, and hopefully you got at least 4 or 5 points out of this. If you did, you're doing really well. I know it doesn't feel like it because you're used to making hundreds, but life is not always going to let you make hundreds. So, what did we do first? What we did first was find the molar mass of compound X. Oh, another thing to know here is that the mean on this question, I don't always have the mean or the average for the question, but back in '86 when everybody else in the country took this test, The mean was 5.18. So if you're scoring near the mean, which means 5 or better, then you're in danger of making a 5 on the exam if you pull that off consistently throughout the year by the time the test rolls around May 2nd. If you're listening to this recording in 2010-11 school year. The AP exam is May 2nd, 2011. All right, so the first thing we had to do was find the molar mass. So this was actually worth 3 points, which is kind of surprising. It was worth that much. So obviously the final answer was a point, but you also got a point if you could convert and realize you needed to convert that into atmospheres, as well as you just substituted the values incorrectly. In other words, you got the expression that had density in the right spot, R, T, and P all in the right spot. So that was 3 points. And then for this next piece, determining the mass of each, if you got one correct mass, that's going to be equal to 1 point. If you got all 3 correct, then that equals 2 points. And then part C was worth 1 point with an explanation. And y'all, this is not the only explanation that would have flown. There's other ways to state what I stated. Many other ways. And then on part D, if you got let me see how they looked at that. Okay, this was worth a point. Doing the subtraction. Oh, getting these up here. This was worth a point. Did I get that right? That's 2 points. Yeah, that's all there was 2 points. And then the final part for that one came from actually arriving at the fact that everything had to be doubled. Okay, so hopefully you're feeling good so far. Let's leave the 80s behind. It was a fabulous decade. Good things happened to me in the 80s. But let's move on into the 90s. And let's look at 1991. We love our molecular formula, empirical formula sorts of problems. And this is yet another. Make a little more room in these pieces. I never know how much, so luckily I can tailor this to how I want it. And I'm going to make it a little smaller again, so I can bring my calculator back. I'm going to clear my calculator because I have a new problem. And let's analyze what they want us to do here. Again, if you have your calculator in your hand, it's probably a 9-10 point kind of question. And this one indeed is a 9-point question. So you are trying to get 5 points if you can. 4 points, still really respectable. All right, the molecular formula of a hydrocarbon is to be determined. So ultimately, I'm going to get that empirical formula business and then hopefully find a way to get molecular mass and then make a comparison. And it'll be a simple comparison where I can double something, triple something, whatever it takes. So molecular formula of a hydrocarbon, that's H's and C's, is to be determined by analyzing its combustion products and investigating its colligative properties. That may be a new word for you. Some people learn about colligative properties in first year, and some people do not. Depends on what state you're in and what the state curriculum is. The colligative properties are about adding a solute to a solvent and changing its physical properties, such as its melting point or its boiling point. And melting point is the same as freezing point, so they may say freezing point instead of melting point. Usually it is freezing point instead of melting point. Okay, so they go on to tell us that the hydrocarbon burns completely, producing 7.2 grams of water, I feel a mole calculation coming on, and 7.2 liters of CO2 at standard conditions, which you can interpret as STP. All right, so they just gave me enough information to calculate 2 sets of moles, and they asked me what is the empirical formula of the hydrocarbon. This is a classic. This happens a lot. Learn this technique. Burn it complete with enough oxygen, go all the way to CO2, calculate the moles of water, calculate the moles of CO2, go to moles of carbon, go to moles of hydrogen, compare the mole-to-mole ratio, you're done. All right, so let's start with moles of water. That's what they gave us first. 7.2 grams divided by the molar mass of water, which is 18.02. You can double check it. 18.2 divided by 18.02 is really close to 0.4. So I'll call it 0.40 moles. Now, it's water. See that too? That means there's twice as much hydrogen in there. If you listen to any of the previous tapes about the lecture things in stoichiometry, you heard me give my gory organ bank analogy. This is like saying the water molecule is a human body, and you're managing the organs for donation in an organ bank, and you've got around 6 bodies on a given day, and each has a pair of functioning kidneys, or they did when they were alive, and so that would be 12 kidneys. So this is like hydrogen is like the kidney, and oxygen is like the heart. So if I have 0.04 moles of H2O, then I have 0.80 moles of hydrogen. It's just twice as much because that little 2 right there. So molar carbon dioxide would equal 7.2 liters. Well, let's jump into since this is a gas at STP. We could take our liters and divide it by 22.4, or we could put this in PV equals nRT. So let's go with this PV equals nRT. So if PV equals nRT, here's the number of moles, N equals PV over RT equals, what was my pressure? 1 atmosphere. What is my volume? 7.2 liters. And that is over 0.0821 liter atmosphere. Mole. Kelvin. A constant side is to carry all the goofy units to make everything cancel out, except what we want, which is mole. And then 273 Kelvin, because that's what STP is. 1 atmosphere, 273. So now my atmospheres cancel. My liters cancel. My kelvins cancel. And I have a 1 over a 1 over a mole, which ends up being a unit of just plain old mole. So that would be 7.2 divided by, I'm going to open a paren, alpha R times 273. If you skipped through some of the first part of this to get to this problem, and you're wondering, alpha R, what are you talking about? Type in 0.0821, use your store button, then type alpha and the R that's above the multiplication sign, and enter to store that constant in your calculator so you don't have to keep typing it in. More importantly, you don't risk mistyping it in. So we come out with 0.32 moles of CO2. Therefore, see, there's only a 1 there. 0.32 moles of carbon. All right, so what do I have going on with my mole to mole ratio? I do not write C.32, H.8. What the typical thing is to do is divide both of them by the smallest, so I'm guaranteed to get a 1 here. So I got 1 for the carbon, then I come back up here and do that, and I get 0.8 divided by, I'm just going to go grab it, this stuff, and I get 2.5. So we're getting closer, but we still don't write C1H2.5. We don't So C2H5 is the empirical formula for the hydrocarbon. So we double both because we want simple integers. So 1 to 2.5 wasn't bad, but we can do better than that. So it's trial and error. You double. If that doesn't work, then you triple. If that doesn't work, then you quadruple. If that doesn't work, then you multiply by 5. But eventually, you've got to get really, really close to integers. All right. So now, calculate the mass in grams of oxygen required for the complete combustion of the sample of the hydrocarbon described in part A. So, mass of oxygen complete combustion. All right. Let's do the stoichiometry. Let's just do it as an equation. There's 2 ways you can kind of look at this. We go through this simple math stuff, but the way you probably were thinking more likely is to just write an equation out it's CO2. So if it's C0H5 plus oxygen, chemical combustion of a hydrocarbon, we make CO2 and we make H2O. So if we try to fix the carbon, we put a 2 here. If we try to fix the hydrogen, we're in trouble because we have a 5 and a 2. So instead, when you get in trouble, you double the area thing. So now that becomes 10 hydrogen. So I'll put a 5 there. And I'll put a 4 there. Hope the oxygen's okay. Come in. And if you save the oxygen for last, put anything you want in front of there because we have even numbers. Don't have even numbers. Yes, okay, oxygen fraction. It'll be alright. I know you're not used to that, but you know, it's gonna work out okay. So, how many oxygens do I have? 4 times 2 is 8 plus 5 is 13. So if I put 13 halves in there, then I'm good to go. So, what did we just figure out? What do we know so far? How calculate the mass in grams? How much of this sample do I have? Oh, okay. I had 0.32 of this mode, and I had 0.40 of this mode. So where am I getting that? Moles of carbon dioxide, 0.32. All right, so see that where I put that in my situation here. And then moles of water was 0.4. So I'd already calculated those. So now let's do the stoichiometry of it. These come out exactly the same. This is not a tricky limiting reactant moment, but I'll do them both just to prove it to you. My way of doing stoichiometry is not dimensional analysis. I look at this as a table, and I'm sitting here with a number of moles. So I would say, okay, if 0.42 goes with the coefficient of 4, then what does coefficient 13.5? What is that going to be? The 13.5 is also known as 6.5. If you like it, you guys will find better than 13.5. So I'd simply take the 0.32 divided by 4 where 1 is, and then multiply that by 6.5. Now come out from that direction and come out with 0.52 moles. But let me prove it to you that it works the other way as well. If 0.4, look at the way. If 0.4 moles goes with a coefficient of 5, then 0.4 divided by 5 is what 1 is. And then I would multiply that by the 6.5. And voila, it's still coming out 0.52. So what I'm trying to trick you for the limiting reactant moment here, either way you went at this, and there are many ways to come at this, you're going to come out with the fact that you need 0.52 moles of oxygen required. Well, that means, if you look at your labs, calculate the mass of grams of O2, then I need 0.52 moles times O2 grams per mole. Right, so that cancels, and I'll come out with 16.6, 16.7, how many sig figs do I need here? Look back at the top. 2, I need 2. So I'm going to call that 17. 17 grams of oxygen required. And again, if you work this a different way, 17 grams of oxygen required, no problem. Because the other way to do it was to say, I had 0.4 moles of water and 0.32 moles of CO2. So my 0.32 moles of CO2 for oxygen gets doubled to 0.64. But for water, because there's a 1 on that O, it remains the same as 0.4. So I needed 1.04 moles of oxygen required. Those would be O's. So I'd cut that in half and come out with 0.52 moles required for O2, and then multiply that by 32, and I still come out with 17 grams of oxygen required. More than one way to skin a cat, my grandma would say. I went the stoichiometry balanced equation route, but you certainly could have done it through the moles route as well, since you already knew moles of water and moles of carbon dioxide. Okay, now here comes the part you may not be as comfortable with. This part may be brand spanking new to you, but you know what? It won't be the last time you learn something new in this course. So we're going to tackle it anyway. And when you get into trouble, there is a formula sheet in the free response that you can look at. So if you'll print that formula sheet off of our website, the WikiPage website, you will have it and you start shopping. And you would find something called the freezing point depression formula. So the hydrocarbon dissolves readily in CHCl3, the freezing point of a solution prepared by mixing 100 grams of this and only 0.6 grams of this. Okay, so when you make a solution, the thing in the smaller amount is the solute, and this is the solvent. Those are words you do know. And the freezing point is 64, minus 64, I should say, degrees Celsius. The molal freezing point depression constant. That's a mouthful for something called Kf. Of CH3 is 4.68 degrees C per molal. I'm going to need that piece of information. And the normal freezing point is negative 63.5. So we only went down a half a degree. It took another half a degree cooler before it actually freeze. So calculate the molecular weight, or molar mass, same thing, of the hydrocarbon. All right, so you shop the formula sheet, or you learn this now. And again, I realize this may be the first time you've ever seen this in your life, and that's okay. The change in the temperature of the freezing point is what Greek looks like. That's what it translates to. And that is Kf, which is the freezing point depression constant, times molality, not to be confused with molarity. Molality is defined as moles of solute per kilogram of solvent. That's why it was important to identify who's the solute and who's the solvent. They gave them both to us in grams, no problem. I have the formula for the solvent, which means I can calculate, well, I don't need that, I can calculate the kilograms anyway. All right, so what do I need to know next? I am in search of, read it again, molar mass. I got to extract molar mass out of all this gobbledygook. So I'm going to expand mole into Kf, grams per molar mass, and that's what I seek, is that molar mass right there, over kilograms of solvent. So I've got some algebra to do before I start plugging stuff in. So I'm going to first simplify this expression, remembering this whole thing is equal to delta Tf. I'm going to move this Kf first and say that that means delta Tf divided by K sub f is equal to grams over molar mass over kilograms of solvent. I'm not going to keep writing the solvent. I'm too lazy. I'm still trying to solve for this. So if I multiply the kilograms by both sides, then I'm going to get is equal to grams over molar mass. I would rather flip it at this point, but you know, there's, again, more than one way to skin a cat. But my algebra teacher back in high school taught me to flip it at this point if I wanted to solve for this. So I'm going to say molar mass over gram is equal to Kf over delta Tf kilogram. I flipped and I switched at the same time. Sides of the equation, that is. And now if I multiply this gobbledygook by grams, that will be gone, and I will have a final expression. Molar mass equals Kf times the grams over delta Tf times the kilograms. It's time to make a decision. You either actually enjoyed that, which would make you, I don't know, somewhere near the same degree of nerdiness that I am, because I kind of like algebra, or you found that torturesome. If you found that torturesome, you need to start a list of things you need to memorize, and this expression right here would be one of them. The molar mass is equal to the freezing point depression constant, Kf times G, over delta Tf times Kg. There's actually a little pattern in there that's kind of easy to memorize. Now, it's just a direct plug and plug. So, 4.6 per molal times the grams of the solute, I remind you, which was 0.600, over the change in the temperature of the freezing point. So I come back and compare these, and delta Tf was equal to a half a degree. It only dropped by a half a degree. So this is 0.5 degrees Celsius Don't worry about the sign on it. Molar mass is positive. For the love of God, there's no such thing as a negative molar mass. And then the kilograms of solvent would be 100 grams, so that's 0.100 kilograms. All right, so this little molal right here is really grams per kilogram. So you can kind of see how this is going to work out. This is canceled. I'll take that back. Let's see if I can come at it the other way. We know that cancels. Okay, so now what do I have? I have molal, which is moles per kilogram. So this M is really mole per kilogram. So you can see where those cancel. And now I get gram per mole. And that's how this works out to be molar mass. It took me a second to do units there. Sorry about that. All right, so clear this. And I get 4.68 times 0.6. I like to get that numerator, divided by 0.5 times 0.1. And I come out with 56.16, which is logical. It's too many digits for what I want, but I'll round it off here in just a second. And I get, that's grams per mole. I'm going to go back and clean up my sig figs. How many do I need? I have 3, I have 3, I have 3, I have 3. I'm thinking 3. So we will call that 56.2. All right, so they just made you go through a whole lot to get a molar mass so that you could go back to your empirical formula, get an empirical mass, and clean this up with a molecular formula. You should be getting the hang of this now. This is really common on the AP exam, even in multiple choice. So C2H5 was where all this mess started. So the empirical formula was C2H5. Therefore, the empirical mass is equal to 2 times 12.01 plus 5 times 1.01, which is 24.02 plus 5.05, 29.07. Molar mass was equal to 56.2, and when we divide that, or let's just multiply it by 2, and you'll see that you come out really close to 58. So it's approximately twice the empirical mass. Therefore, molecular formula is going to be twice. That just didn't come out very pretty. So C4H10. And we are finished. So again, let's go through the scoring. 9-point total. Let's see how that broke down. Way back up here at the top. We got a point for getting the moles of hydrogen from the moles of water. We got a point for getting the moles of carbon from the moles of carbon dioxide. And we got a point for arriving at C2H5. Then, when we came down here, we got a point. No matter how you figured it out, we're figuring out 0.052 moles of oxygen were required, and then a point for being able to multiply that by 32 as opposed to 16, and come out with 17 grams of oxygen required. Then, however you came at this math, we get a point for getting the expression, getting everything in the right place. In other words, setting it up properly, which we often call a substitution point. And then we got a point for actually arriving at a correct algebraic answer of 56.2 grams per mole. And then a point for using your 56.2 grams per mole and comparing it to your empirical mass of 29 and realizing that's just really close to 2, considering these are experimental numbers they're giving us. It's never going to be perfect. All right, let's do another in the 90s. And then I think I may end this recording and come back and make a part 2, because if this goes on too long, my files get too big. All right, so clear. Come here. And let's go to 1993. This one's better. I'm going to copy this. Bear with me. And paste it. And right key effort. Hopefully you're fast forwarding through this and not watching me type. It never hurts my feelings, by the way. Alright, I'm going to need more room. And it's kind of nice if you have the patience to at least glance through these. I'm not saying you have to work every one of them. What I will say is that everybody's capable of learning this. It just matters what the repetitions are. Somehow I got off a 93. Don't know what I did. Okay, I guess I'm going to live with this one. I don't like these little screen clipping things on. So again, bear with me a second. In case you're curious, this software is called OneNote software, and you want it. You want it for college. And my computer is a tablet computer. That's also what you want to request for college. If you have a savings account or kind relatives that will take up a collection for you, this is the best. You can take any document and you can bring it in here. Alright, so let's take a gander at this one. This one is kind of lab-based. This one is also a 9-point problem. Because back in the 80s and 90s, they were mostly 9 points, but now they're mostly 10 points if you have a calculator in your hand. This one was tough. The mean on this one is only 3 points. So why don't you pause at the moment and see if you can beat 3 points. Alright, ouch, because that's painful. We really want it to be closer to 4 to 5 points for the mean. Alright, so give this a shot. I'll wait, you can pause me. Alright, this is a 3-step process, and it is a redox titration. I know this because it says titration. I also know that permanganate is involved, and permanganate is always involved if it's in a titration, in a redox titration. Because permanganate is well, it's not permanganate here in particular, it's manganese dioxide. But the manganesium, that's not right. The manganese ion has a lot of different oxidation states, but it's notorious for participating in redox equations. Okay, so they say the amount of oxygen dissolved in water can be determined by titration. First, manganese sulfate and sodium hydroxide are added to a sample of water to convert all the dissolved oxygen in the water to MnO2, as shown in equation 1. Then the sulfuric acid and Ki are added, potassium iodide are added, and the reaction is represented by equation 2, and it proceeds. Finally, the iodine that is formed is titrated with standard sodium thiosulfate, according to equation 3. So according to the equation above, how many moles of thiosulfate ion are required for analyzing 1 mole of oxygen in distilled water? Alright, so let's think this through. We had 1 mole of the oxygen, which then comes into the second step, and see how that has a 2 right there? We need to double everything in this second step. Because if the second step is really happening, we made twice as many moles of this as we had moles of oxygen, since that has a 1 in front of it. So I just need to double everything here to keep the stoichiometry accurate. They simplified it. I'm going to unsimplify it. Okay, now what? Now when we do that, we realize that, we needed, I'm looking for my manganate ions here. Oh, see that 2 right there? I introduced a 2 on the iodine. So again, with the whole idea of doubling everything. Okay, so that's the real story. They just did them in simplified, easy steps as separate processes because it was a lab. But that's the real stoichiometry. And so to see that, it's obvious from that you need 4 moles of the S2O3. So 4 moles of the S2O3 2 minus ion are required. Now, let's say you didn't catch that. You can still do it by dimensional analysis. Just start off this way. 1 mole of oxygen. There's 2 moles of the MnO2 per 1 mole of oxygen. Where am I getting that? I'm getting that from step 1. Clear this off. See, there's 1 mole oxygen right here and 2 moles there. So I'm just getting that from step 1. And then what happens? 1 mole of MnO2 in the next step. Before I doubled everything, it was 1 mole to 1 mole of iodine. That looks like S2O. I'm done with it, doesn't it? Let's make that a little better. I2. And then, how do I get rid of that I2? There's 1 mole of I2, again, before I doubled it originally, to 2 moles of S2O3 2 minus. So what do you end up coming out with? Cancel, 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 cancel. So I have 1 times 2 times 1 times 2. That would be 4. Divided by 1, divided by 1, divided by 1, that's still 4. 4 mole of S2O3 2 minus ion. So you either look up there and you figure it out by realizing you've got to respect the stoichiometry in each one of those subsequent steps, or you can do it through dimensional analysis. It's your choice. Either way, it was worth a point. And it was a lot of thinking to get that point, actually. All right, so in part B, a student found that a 50 milliliter sample of water required 4.86 milliliters of 0.0112 molar sodium thiosulfate to reach the equivalence point. Calculate the number of moles of oxygen dissolved in this sample. All right, so the moles of S2O3 2 minus are equal to the 4.86 milliliters times the 0.0112 mole per liter. So my liters cancel, and I come out with an answer in millimoles. I need you to start recognizing this as code. This is code for the number of moles. And you can deal with the milli, or you can make them times 10 to the minus 3. I don't care. But I'm going to leave it in millimoles because I'm not a fan of a million zeros or scientific notation. It just slows me down. So 0.0112 times 4.86 gives me millimoles of, it's a small enough number as it is, 0.0544 millimoles of S2O3 minus. Okay, now what? I'm looking at the stoichiometry, I'm looking at what they just had me figure out. Every mole of oxygen dissolved requires 4 moles of the S2O3. So I need 1/4 as much. So therefore 1/4 as many moles of oxygen. Or if you want to actually do it, 0.0544 moles divided by 4. That's why they had me figure that first piece out, so I could use it here. So that comes out to be 0.0136 millimoles of oxygen. And they said calculate the number of moles. So I'll be nice and put it in scientific notation. So 1, 2. Okay, if it's millimoles, it's already 10 to the minus 3, so that makes it 10 to the minus 4, 10 to the minus 5. So 1.36 times 10 to the minus 5 moles of oxygen. Again, where did this 4 come from? This 4 comes from this 4. It comes from this 4 as well. Figuring out that that's the actual stoichiometric ratio of for every mole of oxygen. I'm going to use 4 moles of this thio to actually titrate. Now part C is how would the results in B be affected if some of the iodine were lost before the S2O3 was added. So go back and find the iodine step. So my iodine was generated right here. If some of that is lost and not all of it gets to react, then that's going to require fewer moles of the titrant, S2O3. So less I2 requires less thio. Therefore, lower amount of oxygen reported as dissolved in the sample. Then, what volume of dry oxygen measured at 25 degrees Celsius? Oh, look at that. A temperature and a pressure. Go directly to Kelvin. You're into the land of ideal gas law. 298 Kelvin. 1 atmosphere. So there's my T. There's my T. They want to know volume of pressure would have to be dissolved in 1 liter of pure water in order to prepare a solution of the same concentration as that obtained in B. Okay. Well, I need to know what that concentration was. They had me in B calculate moles. I just need to know what that is in concentration. So let's start there. The concentration of O2 in moles per liter, which is what the square brackets mean, is my answer from B, 0.0136 millimoles. If you like moles better, that's okay. And back up on B, I was also told it was a 50 milliliter sample right here. So that is 50.0 milliliters. The millis cancel and I get moles per liter, as expected. So the number that's sitting there divided by 50 is times 10 to the minus 4 molar. So that's how much oxygen that I have going on. So PV equals nRT. Therefore, the volume is nRT over P, which is my moles I just got, times R times 298 Kelvin, all divided by the pressure of a nice round 1 atmosphere. So atmospheres cancel, kelvins cancel, moles cancel. I love it when volume comes out in liters. Therefore, the volume of this dry oxygen is equal to, let's calculate that puppy. My 2.72 is still sitting there, so I'm just going to use it and multiply it by alpha R and by 298. I'll go ahead and hit enter and get my whole denominator, which is divided by 1, so that is my answer. So that comes out to be 0.0066, dare I say 6 liters, which I would rather see as 6.66, still evil, milliliters. Then, name an appropriate indicator for the reaction that's shown in equation 3 and describe the change you would observe at the end point of the titration. Okay, here's what you need to know. lab is a component of this course. On the official course outline from the College Board, it is 10% of the course outline. So 10% of your time, essentially, should be spent in lab, and you're not allowed to forget every lab you ever did before coming to AP Chemistry, because you did a fair share in first-year chemistry. So if you've ever, maybe even in biology, used iodine as an indicator to test for something, that same something could be used as an indicator to test for iodine. So once upon a time, I'm hoping you performed a starch iodine test. So a starch indicator is suitable. And if you mix starch and iodine together, you get, depending on how strong either of the solutions are in terms of concentration, then you get this bluish, purple, black. It kind of goes the gamut. If it's fairly dilute, then it's blue. If it's more concentrated, it'll go to a darker bluish, kicking over into purple, which could go all the way so dark purple that it's really kind of black. So that color would disappear as the reaction proceeds. Since I2 is a reactant. So again, the color changes between starch and iodine. So if I look way back up to the beginning of this scenario, there's my I2. That would be a reactant. So as I continue to titrate this, that color is going to start to actually disappear. It's going to go colorless eventually. All right, so let's talk about the scoring on this one. Then it's probably time for both of us to take a break. All right, so again, I say the mean on this was 3 points. Just really, really sucked. All right, so whichever method that you use to come around to the fact that I need 4 S2O3 2- ions for every mole of oxygen earned a point, whichever way you got it. So let's say you didn't come to the right conclusion. You said 2. As long as you use that consistently, stoichiometrically, down the rest of the page, you're going to lose this 1 point initially, but you're going to be able to capture some points back on this. It's a pain to grade. Your teacher doesn't like grading it that way, let me tell you. I'm going to make this bigger. Okay, so you have a point if you have the 4. If you didn't, you don't have a point yet. Then if you used your point the right way, or actually you decoded the code here, that 4.86 milliliters times 0.0112 moles comes out to be this many millimoles of S2O3, or moles if you reported it that way, that's fine. Equivalent numbers count. So a point here and then a point here, again, for using your stoichiometry. So the correct answer was 4, so you need a fourth as many moles of O2, but if you said it was 2, for instance, then you need half as many. So however you worked that out, if you did that part correctly, you can get both of those points even though you screwed up on part A. Then, part C, less understanding that and writing a sentence that made sense to go with it, earns a point. Calculating this molarity, this right here was a point. Using that correctly in the right spot and continuing on to put your R in your K, and most importantly making it K, because they tried to trick you giving you 25 degrees Celsius. Hopefully you didn't toss 25 in there because you realized your units wouldn't work. You got a point for that substitution, just getting everything in the right place, and then actually operating your calculator correctly to come out with either the volume in liters or in milliliters. It didn't really matter which one. It just said what volume. It didn't say in liters. And then finally, for part E, the very last part, I think that's also worth a point. Yes. It's 2 points. 1 point for knowing starch, and 1 point for talking about the color change and getting that correct. In other words, you might not have been able to remember it was starch that you used, but you may have done a lab similar to this where the blue, black, purple color would have faded if the iodine was being used up. It would have appeared if the iodine had been a product. So hopefully you didn't get that backwards. Okay, so I'm going to stop this recording, but let me just kind of give you a foreshadowing, because I don't know how much of this you want to listen to. Again, I say everybody is capable of learning how to do this. It's a matter of repetition. I never tortured my students with too many repetitions because Some of them needed them and some of them didn't. I left it up to them to decide. You're big kids now. It's time for you to figure this out. So we still have to work 1998, 2000, and 2003. So we're more than halfway there. But by the time if you're good now, then for the love of God, don't let me waste your time. But if you really need more help, then I am going to do a second part in this recording, in a second tape or second AVI or WAV format, whichever format I'm using at the time. And I'll post both. So thanks for your kind patience. I hope you find these helpful. Remember, you never hurt my feelings if you fast forward. But also remember, I really expect you to work these problems, and I really expect you to be punching the buttons on a calculator. It is not a spectator sport. So hope to talk to you again soon. Thanks.